Okay, so again use these three basically. Okay. Yeah, so we'll start with this. Basically, this is a more general version. This is not the lopsided version. The lopsided is even more general. We saw it briefly yesterday. But this allows the values to have different probabilities. You don't need uniform upper bounds on the probability of happening and the number of neighbors and so on. Okay? So, and the simple idea here is the following. I'll make the statement, but the simple improvement from the symmetric to the asymmetric is the following. Right? So, idea for this again is due to Joel's Spencer, but for those people who know Joel, I mean, he's extremely modest. He doesn't, I mean, writes these in his books and so on, gives these research, but he never says they're due to him. But this idea was due to him. Idea for symmetric to asymmetric improvement, it's a simple but very useful idea. So if you remember, and if you go back and check, right? So you wanted when you did the induction stuff, right? In the denominator,
This is due to Joel.
this is due to Joel Spencer. The co-author of the Alon Spencer book. It's a simple but useful idea. In the denominator, want the lower bound as an example for something like this. So yesterday, not even symmetric, I'm sorry, idea for 4P, 4PD, 3 plus 1 and symmetric to asymmetric improvement is the following. So remember, so you want typically a lower bound for something like this in the denominator you wrote, right? And yesterday, what we did was we said this such a denominator is and then we apply the union bound here. And then we apply the induction hypothesis to upper bound each of these terms. Yeah?
Now you're going to do, let me guess, you're going to do conditional, but
That's-
the value depends on the number of, right?
So today, but now you can do better. You can directly do better as this stuff, the denominator equals the probability of the complement given in 5 times the probability of the complement given E1, E3, E4, E5 all complemented, right? And of course, this is equal to, so let's call, for simplicity, call this A, call this B, so this is of course right? So instead we can do better like this, and now again apply induction. Apply the induction hypothesis using the fact that the number of terms here in A and B is still less than the size of the set S that you started out with in the induction hypothesis. Right? So once you do this, you can get what you want, right? And that's what made Joel wonder why we need the symmetric local lemma. Why not the asymmetric local? And Moser-Tardos gives a full. In fact, you get some. Okay, so I'll state the asymmetric local lemma, right? And then and then the beautiful thing is Moser-Tardos analyzing it gives one sort of new interpretation of the asymmetric local lemma also. So Moser-Tardos is a full algorithmic version of the asymmetric local lemma, the more general local lemma, not of the lopsided local lemma. That was a separate later improvement. But so let me state the asymmetric version of the local lemma, from which the EP d+1 follows as an easy corollary, right? Okay. So what is the asymmetric version of the local lemma? So okay, now let's take the general asymmetric version. This is still not the. I will mention what the lopsided is when I say it. Any questions so far? So as always, please stop me. And in particular, Sohail is also welcome to stop me like yesterday. Okay, so. Given these diagrams E1 through En, and here we are not assuming the variable version. Remember, the variable version is almost all applications of the local lemma include the variable version, where remember what the variable version is. You have some underlying independent random variables x1 through xn. Each EI is a Boolean function of some subset Si of them, right? And therefore, you naturally say that two of them are connected if adjacent, if only EI and EJ are neighbors in the dependency graph, if only Si and Sj intersect, right? We don't need the local lemma doesn't need to assume that. It just assumes that you have some neighbor set for each E, right? Right, so let us set in I and not in I. From yesterday. So again, what we want from this is just recall. Okay, so recall. Non all I for any non-neighbor set. The whole complement. Okay. The probability, this is sufficient. Is equal to, but less than or equal to is also sufficient. And the less than or equal to is the lopsided. Okay. It's a useful exercise for you to, for example, assume this or that and derive the proof of the case of the local lemma. Okay, so now we don't want to, so the asymmetric local lemma says you don't need to put uniform bounds like P and T for all EI, but you can have the EIs have diverse probabilities of occurring and diverse sizes of N of I and so on. Right? Now, here is the asymmetric local lemma. It looks a little bit complicated. Actually, it's not. Once you get some experience with it, it's not. And then the beautiful thing is, Moser-Tardos, when we analyze Moser-Tardos, we'll be able to get some further intuition into the variable xi that I'm going to define next, right? So now again, what do we want? We want a sufficient condition for avoiding all the EIs simultaneously with non-zero probability at this point. So then if problem there exists such that. So okay, so let's say we'll see an intuition behind xi in a couple of minutes. Okay? But right now, what the asymmetric local lemma says is, if for every variable you can come up with a real number xi, strictly positive, a non-negative real number strictly smaller than 1, such that the probability of EI, okay, so this basically, it will be distance. This looks a little bit complicated, but then what we want
This xi is not the variable, no? Hold on.
is not, it's just a scale.
It's this thing.
Okay. So this is the condition that the exercise should satisfy. Okay. Okay. What is this mysterious xi? Okay. Essentially, it is just this. Okay. So now, okay. So this. Okay. So we. Okay. So the way. So now it's a good exercise for you to do this exercise. Okay. First of all, use this idea. Okay. Use that the denominator can be better lower bounded. Let me draw a cloud around this. So that you use. So let me draw a cloud around this to say that this is something we want to use. Okay, so use this cloud idea, simple idea. And show by induction now the size of it, just like yesterday. That for all I not witness, same thing. The probability, remember, this is exactly the sort of thing we wanted to show. The probability of EI conditional on nobody in EJ happening in S happening, right? Is less than or equal to X. That's it. Okay. Okay, so it's a good, it's the same proof like yesterday, except that the denominator analysis, you are a little more careful and you allow these heterogeneous systems. Right? And this stuff, essentially what will happen is this stuff you will write as something like this in the numerator, divided by something like the product in the denominator. So the product will cancel and you get this x, right? That's if you do the same proof as yesterday. Really nothing different except that you use a stronger induction hypothesis, something like this. Yesterday we said 2p, right? We said 2p. Instead you make this a heterogeneous number, right? Xi, and then in the denominator you are a little more careful like this. Right? And this allows you, we will see a high level example of an application. But let's get some intuition now about these xi's, right? Okay, so this is the statement of the asymmetric local lemma, right? Not terribly hard to remember, especially once you get used to it. Although this looks complicated, it's not. It's But one question is, in applications, how do you come up with these little x's? I'll tell you some heuristic ideas. Okay, I'll also give you an excellent reference for a book on the local lemma. So it's not just on the local lemma, but okay. So let us. So I'm going to erase. Let's start with erasing the leftmost. how to come up with these xi's. First, let us recognize.
Sorry, let me, and you've dropped do you also need the top assumption? Or you dropped it now?
Which one?
That the probability of EI conditioned on not EJ.
This is necessary because this defines the sets Ni, right? The Ni's. So you now have some abstract. You have
Okay, got it. This is the independence from the far away.
Yeah, this is the same as yesterday, right? This is the same as yesterday. This is the definition of the
Yes, and
dependency graph.
the proof you use this when you estimate the numerator, right? If I'm not mistaken.
I'm sorry.
In the proof we use this when you estimate the numerator,
Use
the top one, the independence one.
That's it. That's it.
Okay.
That's
Then
when you talk about the numerator. And since you only want to talk about the numerator, this also suffices. That's the idea behind the lopsided version. Okay? And like I said, the lopsided version is also quite helpful. For example, for the latent transversals problem on n by n arrays that we saw yesterday. Okay. So first, let me quickly derive the symmetric local lemma as a corollary. Because remember, yesterday we only showed this, right? We only showed this 4PD. Let's easily recover this. Right?
right now there will be some condition which depends on the size instead of P.
Yeah. So now basically we'll take all the xi's to be a common x that's all. In the symmetric version, right? That's it. So all the x. Okay. So how to select these mysterious xi's? There are a few recipes that work.
But also the D now depends on XI, the D that I'm allowed, I have now a DI.
D is the maximum cardinality of any,
Right, but I could just take DI to be the cardinality of NI, and do I get now an expression? Right, so I would imagine that maybe you can now get an expression that would say the sum of all I of XI DI has to be at most something like this. Fine.
So where do you want to, you mean as a corollary of this?
So there's this assumption that says that EP D plus 1 has to be at most 1, right? I'm expecting that now I will see some expression that involves the size of NIs instead of just a uniform D, and the XIs instead of a uniform P.
So that is this version. So this is the more general version. We are going to derive the symmetric local lemma as the EPD plus 1 is a simple corollary of this.
Yes.
That's all.
Oh, I have no more assumptions, so I see. Oh, I see. That is just the only assumption that I need to mess with.
Yes. So, yeah. So how to choose this? So we'll keep this part of the board for a while. Okay, so how to choose the XI's? Right. So one, the symmetric case. So here right? This is the symmetric case, right? So set of xi equals to some z for some z. What do we want from z? What we want, it suffices if the probability of EI for all I, which is less than or equal to P, is less than or equal to z times 1 minus z to the power of d. Right? So if you make all these xi's equal to some z, this becomes, this is at most, there's at least z times 1 minus z to the power of t, because the number of terms in this product is at most d, right? So and for all I, you know the probability of ti is less than or equal to p. Therefore, it suffices if there exists a z that satisfies this condition, right? Z is a function of P and D, right? So Z is a parameter that you want, right? Suffices it, this, right? Now, how do you choose the optimal T? Just find the, so you want the maximizer of Z, where Z runs from 0 to 1, right? So in particular, what Z should you pick? You should pick the maximizing Z. Maximizing Z is equal to 1 over D plus 1, right? Therefore, it suffices if P is less than or equal to 1 over D plus 1, 1 minus 1 over D plus 1 to the power of D, right? Right? And this is greater than or equal to 1 over E. Therefore, P less than or equal to 1 over D plus 1 times 1 over D suffices. In this symmetric case, this is exactly the version that we saw, right? E times P times D plus 1 is less than or equal to 1. Right? So in the symmetric case, you just choose the easy, we can easily set all the xi's to be the same uniform value. Which uniform value Z will you pick? If you want this condition, clearly you should pick the Z that maximizes the right hand side, which is 1 over D plus 1. Right? And then you get this. Right? So you of course recognize the symmetric case easily from this thing. Right? Otherwise, let me give you a nice book reference. It's about 25 years old, but I think still very good. Okay, so okay. What about otherwise? Otherwise, there are some recipes. More generally, you can try out some recipes. Typically, some of them work. Other recipes for pizza. Okay, this is from the book. Check out this book. Graph coloring and the probabilistic method by Moser and Aravind. This book has an amazing, it's around 25 years old now, maybe even a little bit more, by Moser and Aravind. This book has a whole host of probabilistic ideas on a whole range of graph coloring problems. The local lemma plays a heavy role in many of these. Okay, I can talk for quite a while about the book and some results in it, but let's not. But in particular, I will just mention the following. One of the powerful techniques in probabilistic combinatorics, which is continuing to play an important role, is what is called the nibble method, right? It's also described in the Alon-Spencer book, right? And here, in fact, I will very briefly say, when talking about one of the major applications of the asymmetrical LL, I will mention the nibble method a little more, right? The nibble method is often, if you want to do a random construction, to do it in slowly in multiple steps. You take some steps, use them, for example, the local lemma to show that there is a good choice for that step, fix that, right? And having done that, take a small second step, again, having fixed the first step to something, use the local lemma, for example, to show that there is a good choice for the second step, fix that and so on. Do it in a large number of steps, right? In Ramsey theory and so on, this is very helpful, but more generally, very, very helpful. So that is a really nice, the book has a whole host of results, descriptions on martingales, the local lemma, and a whole host of coloring problems. Really terrific stuff. Oh, I'm sure, of course, a lot of the results have been improved in the last 25 years, but it's a very good reference book. Okay. So this book gives some other recipes, right? So note, first of all, from this, right? Note from this requirement that we have, now this stuff is of course less than or equal to 1, right? So of course xi is greater than or equal to the probability of of course, right? Note of course that xi is greater than or equal to the probability of So some recipes that work in applications, right? Or for example, xi equals the probability of AI to the 1 minus epsilon small enough. Okay, so that depends on the application. Or xi equals for some fixed c, like c equal to half or 1/3 or something. And there are other recipes also they show that work in various applications as suitable choices for the xi. Okay, so there are you need to figure out what potential xi could so essentially think of xi, of course, is greater than or equal to pi. How much greater should it be depends on the application. Okay, so there are other such recipes that you can try out. There is no, of course, universal recipe. You have to given the problem, you have to check it out. But of course, the easiest case is the symmetric case where you can fully derive the essentially optimal xis. Okay. So keep this in mind. We'll get a new interpretation of the xis when we analyze the algorithmic version of the local lemma, which is due to Moser-Tardos. But before going to that, I want to show you a really nice application of the asymmetric local lemma, which again is originally due to Joel Spencer. So, and this is in Gramscian theory. So let me erase these two values. Recall one of the basic statements from Ramsey theory, which is that there indeed exists such a minimum n. This number n is finite, right? And RKT, I mean, you can also define such things for hypergraphs and so on. We are only talking about graphs here, right? Recall Ramsey's theorem that so in particular, the original Ramsey theorem is that RKT is finite and it's at most something like this. K plus K minus 2 divided, we'll choose K minus 2. So this is a simple induction you can do by induction on K plus T. You can easily prove this. It's a good exercise. So it's a basic result in Ramsey theory. Every n vertex graph, right? Either has three k vertices or an independent set of k vertices, right? In particular, RTT, if both is less than or equal to 4 to the t, right? This is due to Erdős and Szekeres from the 1930s. Right? And of course, the famous lower bound of Paul Erdős by the probabilistic method is that this is greater than or equal to root 2 to the power of t. Right? This is due to Erdős in one of the papers that is said to have initiated the probabilistic method. Right? In other words, what does a lower bound on RTT mean? It constructs a graph. There may be a constant c here. It's not important, right? It's the base of the exponent that is important, right? If RTT is, let's say, greater than this, what this means is that there exists a graph with this many vertices, which contains neither a clique of size t nor an independent of size t, right? If RTT is greater than this, right, then by definition, what that means is that if you parse this definition, it means there exists some n vertex graph where n is equal to this quantity on the left, such that this graph has neither a clique of size t nor an independent set. By size, I mean number of vertices, neither a clique on t vertices nor an independent set on t vertices. And of course, the way Erdős showed is, he took this n and constructed a random graph, right, where every edge is present independently with probability half. It's a standard Erdős linear graph, and then he shows using a simple union bound that there is neither a with high. You only need to show with positive probability, but in fact, with high probability, there is neither a clique nor an independent set of size t in this graph. Therefore, RTT is greater than this. Here again, the local lemma can play a small role. It can improve this constant c improvement, right? But there are other ways of doing it. But anyway, there are even further improvements. But this, I will. Okay, so I'll tell you where the case that we consider. We will not consider this case.
So are you telling us that the asymmetric lemma will get a better base of the exponent?
Oh, no, this is the base of the exponent. This constant c can be improved slightly using the local lemma. Okay. But this is not the main case we're going to talk about. This is, you can think, okay, I'll say something just a little bit more about this, right? We are mainly going to talk about the case when k is small, like 3, and t is asymptotic. And that's where the asymmetric, and I'll give you at least a high level idea of how to do it. But let's just complete this discussion, right? So a fascinating open question, of course, has been to show what the correct base is. Right? And I mean, a reasonable conjecture could be this is 1.414, this is 4, maybe that it should be something like 2. RTT, should be something like maybe some 2 plus little o of 1 to the power of t, right? When t is an asymptotic parameter. And recently, there was some huge breakthrough by Campos et al. There's a group from Brazil and the UK around 2023. Approximately 2023. Now with some further improvements, it's something like maybe 3.83 to the power of 2. So this was a huge breakthrough. By the way, Johan Wigderson, Avi Wigderson's son, he is a postdoc at ETH Zurich, and he has a Bourbaki seminar on this. So he's written very detailed notes on this. So check out. See Johan Wigderson's Bourbaki survey on this. This is not the case we're going to be interested in. When this came out, Johan Wigderson was interviewed in a Quantum magazine article, and he said, when I heard of this, I remained excited and breathless for a whole day, basically. I mean, it was such a breakthrough. Now that this barrier has been broken, it's conceivable that it can come down to even much lower, maybe approach 2 or whatever, right? And the lower bound is still remains, right? Yeah, but I just wanted to tell you that it's of course an important, one important special case is the case where both k and t are the same. That's not the case we're going to talk about. I just wanted to mention that there's all this beautiful stuff there. I want to consider the case where k is small, like 3, okay, and you again want a lower. You can again, okay, yes, so you can think of this as the diagonal Ramsey number k equal to t, and you want very much the off diagonal Ramsey numbers, right? Let me at least give you a high level idea of how you can, just like Kurdish had a probabilistic construction for this, we are going to give a probabilistic construction for a lower bound of R3T. The upper bound you can always use this, and these upper bounds, are not generally, are not always tight, as you see here. Okay, so let's consider R3T, where T is now the asymptotic parameter, right? So in other words, you want to get a lower bound of R3T. In other words, you want as large an n as you can, and you want to show that there exists n vertex graph that neither contain a triangle, right? So k equal to 3, neither contain a clique with 3 vertices, that is a triangle, nor an independent set with 3 vertices, right? You want to show that there exists such a graph. So natural idea is to do a random construction, which is what we will do. Okay. But this is the one of the very important cases, the diagonal case. I just wanted to mention this, and I really enjoyed reading. I presented this briefly in some class. I'm not fully understood this, but by the way, Yvonne Peterson also has very good notes on Ramsey theory. If you so. Okay. So we'll briefly see about using this for lower bounds on R3T. Okay. Okay, this is so expensive around 1977. It's been improved, but let us see what the thing is, right? You will see that without proof that this is what this gives. It's of the form n would be of the form t squared over log squared t. Take the random graph G to be the random graph G and P. So which is where Srini take in vertices, each edge put independently with probability P.
So, okay, so let me try and just kind of settle myself into the proof you're about to make. So now you're going to give us some conditions. They should, if they're all false, it should imply that there's neither no 3-clique nor independent set of size t. And then you're going to give us these values xi, and you're going to prove that bound, right?
So we won't have time to prove, but yeah, this is what the paper is, right? And we'll see conceptually what the idea is. It's exactly what you said. Right? Take this graph, right? What you want with positive probability no event of the form clique these are at bad events now. No,
So the bad events are just
clique and independent set events.
What you know, the events function.
Yes, that's it. Yeah.
Is not the event.
Right? There are n choose free sets S of size 3, right? Right? So take n vertices, we'll pick n appropriately, and it will turn out that this calculation gives you t squared over log squared t, right? And we'll walk and construct this. Imagine constructing this random graph where p is to be chosen. So judiciously, right? Now write your bad events. A bad event is for every set S of size 3, there are n choose 3 of them. There is a bad event that this graph contains a clique on those 3 vertices. Similarly, for every subset T of the vertices with size T, right, you get an independent set. There are n choose T of these, right? So basically, you have this, right? So for instance, so we know of course that for all S, the probability of CS is PQ, and for all T, the probability that you gets is 1 minus P, the power of P choose to 2. So just think about this. Right? So I need to switch to Moser-Tardos, which I'll do within 5 minutes. Right? These are your values, and you want to show that none of them happens using the local lemma by analyzing. So, for example, right? I mean, this CS, if S and S prime, for example, if S is 1, 2, 3, and S prime equals 2, 3, 7, then CS and CS prime depend on each other, right? Because they both contain the edge 2, 3, right? But if, for example, they only share a vertex, or they don't even share a vertex, if they share only one vertex or don't even share a vertex, for example, if S is like this, these 3, and S prime is those 3, S and S prime are independent of each other because they don't share any edges in common. Similarly, you can look at the intersection structure of these, right? And in fact, you can, instead of all these Xi's, for every one of these, you can have one X, right? And similarly, for all of these, you can have one Y, right? These Xi's, you can take, by symmetry, you can take Xi to be the same for all these, for all the n choose T bad events of this type, let's call them Y, and then you want this, and then you want some simple inequalities among X and Y, and you want to, show that if N and P are chosen judiciously, there exists, these X and Y's that satisfy the asymmetric local lemma. Therefore, there exists such a graph on with positive probability. Therefore, there exists such a graph. Therefore, you'll get a lower bound. You'll get a lower bound on R3, right? Just like earlier probabilistic construction gave a lower bound on RT. That was much easier. This is more sophisticated, and this gives you this, right? What is the state of the art here? What is the state of the art? So this is the broad idea. Okay, so let's not go further into proof. This is the broad idea. Okay. Yeah. So in the interest of time, I'll just quickly say what is known. So it was known that okay. So now.
And P, I suppose, also needs to be.
Sorry.
And P will also need to be chosen somehow. Criteriously, I guess.
T is given to you.
P,
yes, N and P have to be chosen judiciously. You want N as, you want to choose N as large as possible, and a suitable P that satisfies all these conditions, right?
Is there some kind of matching upper bound?
Ah, very good. Okay, so this was known. P squared over log T was known. And then this gives you something like this. Okay. And then around the year 1995, Jiang and Kim, using the Lemma method and pretty sophisticated probabilistic method, and the local lemma and so on, Kim showed the optimal log norm. Again, using the probabilistic method. So therefore, R3T, its order of magnitude is now determined. Its order of magnitude is really P squared over log T. Okay. There is much more slow progress on R4T and so on, but there's been impressive progress. Actually, R4T has been very good progress. R4T is of the form T cubed over polylog T. The polylog is not determined, but R5T and so on, the upper bound and lower bound are somewhat far away from each other. So let me, by the way, I'll just conclude this part of the discussion by saying again that Joel Spencer has been very interested in these, and he showed that Kim's approach can be simplified using a differential equation approach also. Right? Many stochastic processes can be analyzed using differential equations, and Joel showed that there is a nice differential equation interpretation of these also. Okay, so let's not spend more time on this. Okay, I just want to tell you that there are natural situations like this where these EIs have heterogeneous probabilities of occurrence. Right? Notice that these events have probability like P cubed. Those other events have very different types of probabilities like that. The dependent structure is also different. And there are many, many other such applications where the bad events have heterogeneous probabilities of occurrence. So it's useful to keep the generalized, the asymmetric local lemma in mind, along with some of the recipes we saw of how to select the x's. Right? So now let me switch to Moser-Tardos, which is the algorithmic version of, let's say, the asymmetric local. Right? Okay, so now suppose you are given, right? And the beautiful thing to me, I think that people who understand it better than me have an even better interpretation. But the beautiful thing for me is analyzing the algorithmic version due to Moser-Tardos gives you new perspective on the exercise themselves. Right? So it's really very, very nice to me. And furthermore, analysis shows to you that you can even improve this a little bit. Okay? So let's see what happens. So let me move on to the Moser-Tardos algorithm. But the Moser-Tardos algorithm works as stated, works only for the variable version. Okay, let me remind you what the variable version is. And right now, the variable version is that you have some underlying independent random variables x1 through xn, and each EI is a Boolean function of some subset Si of those variables. So let me write that. I'll briefly say what Moser-Tardos is. It's exactly what we saw yesterday. And then we do an analysis, which is, in my opinion, quite illuminating. Any other questions so far? Okay.
In the case of variable version, I mean, we have exact prompts on what expressions on what means the EI is.
Each EI is just some Boolean function of some subset of the underlying independent random variables. That's all. Does that answer your question?
Yeah, I mean, in terms of what the function is, we can.
It can be arbitrary. EI is an arbitrary function. Okay. Okay, so let's write the variable version. Let's write Moser-Tardos and then we'll analyze it.
I have a question. I don't remember what you said. So what is pretty curious, you said a minimal n such that every n-short-fixed graph is equal or an independent set.
K vertices or an independent set of K vertices?
I only know it by your color rates. Good.
Good. So, good. So Florian, So Florian's point is, So equivalently, you can think of taking the complete invertex graph and thinking of coloring the edges as red and blue. Right? Just interpret red as the edge existing and blue as the edge not existing. Right? So a red subgraph, a red clique with k vertices is a clique in the graph with k vertices. A blue clique in the graph with t vertices is a blue independent, is an independent set of t vertices. Right? Yeah, Ramsey theory is often, instead you talk about, first of all, you can talk about hypergraphs, and you don't need two colors, you can have more colors. But when there are two colors, there's a natural interpretation. Color red says that and then you talk about complete graphs or complete hypergraphs, but complete graph, two coloring a complete graph is the same as saying these edges existed. Two coloring the edges of a complete graph is the same as saying that the edges with color red are actual edges, the edges with color blue are not edges. Right? That's, so it's equivalent. Yeah. Yeah. So if you look up Ramsey theory books, they'll talk about, for example, in the graph case, they'll talk about two coloring the edges of the complete graph, which is the same as constructing an arbitrary graph on n vertices. Okay, so again, let's recall what the so the save space, let me say this. Recall that the variable notion is that you have some independent. It's to x and k can diagonals in any set. Right? So recall the variable notion. But by variable notion, we simply mean that there are some underlying variables which drive our values, right? Right? And so what is an algorithmic version of the local lemma? Okay, so now you are given this setup and you are promised that there exist these xi's, little xi's, sorry. Don't confuse these little xi's with the capital Xi's. An algorithmic version is, say, a randomized polynomial algorithm, which in time polynomial n and n will give one value for each of the underlying variables that together guarantee that none of the EIs is true. Right? That's what an algorithmic version is. Right? You want to assign one value to each of these to your underlying variables that ensures that none of the EIs is true. I'll tell you some other exciting frontier things which we won't have time for. Right? Notice that the output size of such an algorithm is just n. So in principle, one can even ask, what if this number n is even super polynomial in n, right? And suppose the EIs are defined implicitly in some manner, they are not explicitly written down. Can you come up with an algorithm that is just polynomial in n, even if this is super polynomial, that guarantees this? There are applications like that also. So most of Moser-Tardos will do it, but yeah, so there is further work. For example, Bernhard Huntler, Bernhard and I have a paper that does it, and there have been further improvements.
But is there like a general theorem or?
Yeah, there are
more
theorems. It's like assumptions, but for example, look at my student David Harris's thesis, right? That's already now 10 years old, but that had I mean, he really did a lot of work. That's a good source, but there are, his thesis and Dimitri's Akyurtas, who's in Athens, together, if you look up their papers.
That was like square root of n or am I misremembering?
Oh, that is the runtime for the Latin transmissions problem.
Ah.
But in general, his thesis is a lot of such research on the local level, algorithmic versions of the local level.
Is there some kind of bound that depends maybe polynomial in n, but only polylogarithmic in n?
So there are under some further assumptions. For example, if instead of this, if you had the whole right-hand side to the power of 1 minus epsilon, you can do all kinds of stuff. Okay, so there are other exciting frontiers also that I won't have time to touch upon today, but that's why I said that Moser-Tardos was already a breakthrough. What does Moser-Tardos do? It runs in time polynomial in N and N, right? And constructs, it's a randomized algorithm that constructs values for these that avoid, that it runs in expected polynomial time, right? And avoids, all of the EIs, but you can analyze it more, and its stochastic properties are very interesting. I'll maybe give you some pointers to look up on additional material, but yeah, this is not the end of the story at all. This was already a massive breakthrough, but people found that more could be done with it. Really amazing. But for today, we'll just analyze, we'll take this setting and we'll analyze define and analyze Moser-Tardos. Okay, so Moser-Tardos is just this. It's a resampling algorithm. What's the time? Wow. Just 12. But also because most of papers from stock 2009, it doesn't have the general version, it has a different information theory. So that's also quite interesting. Is drawn by. So the capital X's are underlying independent random variables. Whenever we say sampling or resampling XJ, this algorithm, we simply mean use distribution DJ and independently of all of the choices, right? So you always generate every sample of XJ for any J independently using its given distribution, right? Always independently of other choices from its given distribution. Now, the algorithm is extremely simple. This is it. Okay, this is all the algorithm is. And of course, when it terminates, by definition, you have avoided all the variants, right? This is the Moser-Tardos algorithm. Maybe the simplest algorithm you can think of. Right? While initially we do a zero sampling of all the XJs, and keep in mind that we always sample independently from the given distributions. And if none of the EIs is true, we are very happy. But while there exists such an EI, pick any one of them arbitrarily, any one such EI, and just resample all the variables it depends on. And that's it. It's simple as possible. Okay, here it's now people know that it's highly parallelizable, it can be de-randomized, there are all kinds of stuff that's new, right? It's really pretty amazing. Okay, that's it. Right? So what do we need to show? We need to show that the expected, so the expected number of iterations is small, right? That's it. And of course, like Bruno pointed out yesterday, if you resample, remember, right? So if you resample here, you'll probably fix, because typically you think of these as relatively small, right? Certainly less than say 1/10 or whatever, certainly less than some constant, some appropriate constant, right? But not terribly small that you can apply the union norm. That's the point, right? So these are reasonably small. So suppose this is probability P, right? If you resample once, already the probability that you fixed it is 1 minus P, right? Because if you resample its variables, the probability that it does not happen is 1 minus P, which is close to 1, right? But of course, those variables can influence other EI prime, and maybe EI prime gets triggered because of this, right? So this is the problem. But we will show that this is not the case. In fact, here is the theorem. The theorem that we put now. Let these little xi's be given to you. So, I mean, the algorithm doesn't need them, but let these little xi's be as guaranteed by the local lemma statement. Right? Now, this is the theorem we're going to show. Of course, therefore, by the linearity of expectation, therefore, the expected number of iterations is equal to, by the linearity of expectation, it is this. Now, the xi's are typically well bounded away from 1, right? So the denominators are all, the denominators will all be at least a half or something. The xi's will never be, in typical applications, they'll never be close to 1. In particular, right? One of the exciting things we showed is that, in fact, in essentially any interesting case, this is almost O of n. That's something that we later showed, right? But don't worry about that, right? Typically, the xi's will be, say, much smaller than half, for example. Okay? So therefore, each xi over 1 minus xi is bounded by a constant. So the whole thing is less than or equal to O of m typically. Let's not worry about m being very large and so on, right? But this is the main theorem we want to show, right? Whatever tie-breaking rule you use here, right? You use some tie-breaking rule, right? If many EIs are currently true, you have to pick one of them arbitrarily to fix any tie-breaking rule. Regardless of that, the expected number of resamplings for any particular EI is this. So this is the theorem we're going to show. And in fact, the beauty of the theorem is it helps us, get this, and in fact, even improve upon it in some cases. So it gives you some insight on the inequality that the asymmetric local lemma has.
That the asymmetric local lemma was proven before in Moser.
Yes. Okay, but this is it. This is the theorem we're going to show. Okay? We can show the full theorem, the full proof. For this, we need one equivalent way of thinking about this, right? Which is the following. Right? Equivalently, just for the purpose of analysis, you can think of equivalently. You can think of resampling the xi's as the following. Imagine that you have a table with countably infinitely many columns. Imagine that you've done the following. Imagine that you have a table with n rows, right? And countably infinitely many columns. such that you do the following. For x1, imagine that you have drawn IID from the distribution D1 infinitely many times and you put them all here in the first group. Similarly, for x2, you do this and so on. Okay.
What? When you put a stone?
I'm sorry.
No, I didn't get it. Sorry.
Sample x1 countably infinitely many times and put those values down. Imagine that we have done that, right? Then imagine that the way we run this algorithm is initially we use in the first step you do this and advance a pointer here, right? And every time if you need to sample x1 again, you use this value and advance the pointer and so on. Right? Imagine that a table has been populated like this, okay? With infinitely many columns. Right? So the resampling equivalently we can think of as just use the next value from the corresponding row. That's all. Okay. So keep this in mind. Right? We of course we equivalently think of this view. Okay. So now here is what we want to do. The key idea is to define a notion of witness tree. Right? And here is where Don Knuth also connected this with some of the interesting combinatorial ideas. You can look it up in the latest book that he's writing. Okay. The key thing is the following witness tree construction. So think of this as iteration 0, the 0th sampling, and then these are iterations 1, 2, etc. Okay. So if you're very, very lucky, you'll be done with iteration 0, but more realistically, we'll need some number of iterations. Right? Now we are going to construct some witness trees. Right? What we are going to do is, we are going to separately, for every one of these iterations, construct a witness tree, and they're all vertex disjoint. Okay. For iteration, okay, you ran this for iteration 1, maybe because you have to resample for E5. We're going to construct a witness tree. Okay. Then you needed one more iteration, let's say for E7. So you went on to iteration 2, you will construct a separate witness tree. Then, unfortunately, you have to go on to witness tree, you will build a separate witness tree and so on. So you build one witness tree during iteration 1, a separate one. You're not going to build on the first witness tree, but build a separate second one for iteration 2, a separate witness tree. Normally witness trees you think of as starting at iteration 1, you're growing a tree, don't do that. At iteration 1, you constructed something, keep it aside. At iteration 2, using the process I'm going to describe, construct a separate tree. At iteration 3, construct a separate tree. All of these are vertex disjoint. Okay. So they're completely different from each other. How do you construct the witness tree at iteration T? Okay. So
Maybe at the
sorry,
maybe you want to tell us at the beginning? Yeah.
I'm going to say what else. This is separate from, it's completely separate I'm going to do this, it's going to be a rooted tree, okay? And I'm going to go backward in time. This is a time. Okay. I'm going to construct a rooted tree by going back in time. Right? Time going down, right? So here I'll start with, suppose we resample for EI in iteration T. So I'm showing you take time t equal to 20, for example. At time 20, at iteration 20, we resample for this EI. So we're going to construct a separate witness tree here with root EI. Okay, why? How are we going to construct it? We're going to inductively construct it by backward induction on time. Okay, right? We're going to now grow the tree. Okay? How are we going to grow this? In the following way. At time E prime, suppose. So here is, so you recursively keep constructing this tree, keep expanding this tree, and now you come to say t prime, say t equals to 20 and t prime equal to 7. And suppose at this time you resample for ei prime, right? And so far, up to time t prime plus 1, you have constructed some tree so far. Okay, so you have constructed some tree with root equal to ei. Okay, so rooted tree, right? Now you're going to, and so yeah, each node will be a label, will have a label saying which event it was. Okay, so the label of the root is ei or I. Okay, so now you have this new node. We're going to attach this to the tree in the following. There are two cases, right? So notice that okay, so we'll say that the dependency graph will say I is a neighbor of j if and only if I'm not equal to j as they intersect, right? Right, this is the neighborhood, symmetric neighborhood relationship in our graph, in our dependency graph, right? Let's call it, let's denote it by I adjacent to j in our undirected dependency graph, right? Okay, good. There are two cases, right? The less interesting case is that this index I prime is not adjacent to any node in the tree. Yeah. So suppose the tree so far has E20, E5, E7, E9, maybe E20 can appear multiple times also in the tree, right? But suppose this is whatever E53, and 53 is not adjacent to any node label you see in this current tree, right? That's the easy case. In that case, you do nothing. You come down to T prime minus 1. Do nothing. Okay.
So you don't put it on the tree.
You don't put it. You just leave it as. Yeah. The interesting case, of course, is that this index I prime is adjacent to some node label in the tree.
So meaning that this node will simply be thrown away. It's just not part. You just throw it. Okay, that's case. Okay.
The interesting case is that it is adjacent to somebody. It can be adjacent to multiple inputs. Now, here is the key thing. In that case, make it a child of the deepest such node, right? Suppose ei prime is adjacent to that node, and this node. Make it to a child of the deepest such node. And if there are many such, pick one dimension. Okay. At time t prime, we'll do the following. If I prime not adjacent to any label in S, if I prime go to the previous time, that's it. So just know, go to the previous time, you're going back in time, right? The more interesting case is, otherwise, make this new node a prime a child of the deepest node in the current tree. Let P be the current tree. This is the definition, okay? Okay. This is how you construct witness trees. So separately at time 1, you construct a witness tree. Separately at time 2, an entirely different witness tree. At time 3, a separate witness tree, and so on. Okay. Okay. So at time 1 you do this, at time 2 you do that, at time 3 you do that as well. Okay. Now, in the interest of time, let me so I'm going to erase the algorithm description itself. But please keep this picture in mind, this table, infinite table picture in mind. We'll need it for one of the lemmas. Okay. So okay, we just need to prove this theorem, right? I'll rewrite this theorem. Here is one simple lemma. I mean, some of these are simple. So if I got resamples. So notice importantly that you don't put any time information on the trees. Okay, every tree is just a rooted tree with a node label index that indexes some one of the values. There's no time information. You're not saying at time t because you have to count witness trees and you don't want to put extra information. Okay, because then the number of witness trees will blow up because you have to take you have to keep track of time and so don't do that. Just put this tree, put that tree, and so on. Okay. If here I got resampled 8 times.
That's the day.
Sorry.
No, sorry.
We'll get a different witness trees with root ER. Why is that? Right? That's easy. Let me just say the proof quickly. Suppose not. Right? That means that, for example, suppose EI was resampled at time 3, right? And resampled at time 7. You're saying that the same witness tree came both, right? So I'm saying that the witness trees all have to be different. But that's easy because suppose at time 3, you got this witness tree, whatever, put some stuff there. And at time 7, right? You will start one witness tree with root here, right? But when you come, normally, I think that the witness, okay, so suppose here I got 3, okay, let's not make it 3, let's make it a larger number, like say 6 and 11 or something. Yeah. At time 6, you constructed this witness tree. Suppose for a contradiction that the witness tree that you constructed at time 11 also was exactly the same. Okay. By the way, there is no left child, right child distinction.
No, it's just the number of VIs is different in all these trees.
Exactly.
Right, that's it.
Why? Because
Because it
if you
appears.
when you come down to time 6, right? There is an EI. At minimum, you can make it a child of the. Oh, by the way, sorry. If okay, so we have to be a little careful. This adjacency relationship now is an inclusive adjacency relationship. Okay, so let's say
Includes I itself.
yeah, let's call it I plus or something. Inclusive. If I equal to j or if this is inclusive relationship is a reflexive. Okay. This is now a reflexive operation, so I put a plus. Okay. So you see, when you come down to time 6, right? You certainly will make this EI a child of that, right? And then furthermore, you build this tree. Right? So the witness tree at time level, because of EI, will have to be strictly larger than the witness tree at time 6. Right? Because certainly, when you come down to time 6, this EI may get attached to somebody, but certainly, if nothing, it can get attached to the root. Right? Therefore, first of all, you want to count the number of resamplings per year. Therefore, we just need to count the number of witness trees per year. Right? Therefore, a corollary, right? So it's an easy, but please keep in mind that here, in fact, you want the inclusive relationship. Right? They reflects the closure of the graph thing. Okay. So therefore, the corollary is corollary. The number of resamplings. Okay, so what you want by the linearity of expectation Right. So with the linearity of expectation, the expected number of resamplings per year is just the sum over all fields, all possible trees with root EI of the probability that EI, the T occurs in our list of WTs. The amazing thing is there is a very nice expression for this. That's what, let's see, using the interpretation we had of an algorithm as pre-populating the table with infinitely many columns and just picking. Okay. So here is a very nice lemma of Moser-Tardos. Right? Therefore, you just need to focus on this counting problem. And the counting problem is made somewhat easier by giving an explicit expression for this problem. Okay. So here is a beautiful lemma. This stuff, which is what we care about, right? In fact, it is so nice. By the way, the trees don't have any left child, right child thing, only parent child relationship. Okay. Then the probability of T is simply the probability of T1 the whole square times the probability of E2 times the probability of E3. Isn't this amazing? Let me show this to you using an example. Okay. So an amazing thing is for every tree, the probability that it appears is simply this quantity. That's it. Take all the nodes. In this case, E1 appears twice, E2 appears once, this appears, E3 appears once. So just do this. Right? I claim that this is the exact probability with which this tree T will ever appear as a witness tree in our list of witness trees. Right? It's really beautiful.
Okay.
Why? I'll just show you by an example. And here is where reinterpretation of our algorithm with infinitely many columns will be helpful. Let me show you an example. Okay, so that will already tell you exactly what this is.
I guess you can use the other board. I'll just move the camera.
Okay.
I don't want to canvas.
Okay, so I'll show you an example. Okay. In fact, here. Simple example that will show to you what's going on. Consider this, okay? Yeah. Consider this tree, right? You just do a depth first search, breadth first search from the bottom to the top. So take the tree. Okay, this proof by example will suffice for you. Okay? So consider 5 variables. Okay, x1, and suppose you just have these 5 and consider these variables. Just as one, I'll just show my example on a tree, on a single tree, and you'll see what the idea is. It's very simple, very beautiful. And suppose, take a fixed tree, okay? Consider this tree. It has just 3 node tree, okay? Here, there is no left child, right child relationship. So consider just this thing, okay? I'll show to you where EI depends on x1, x2, x3. This depends on x1, x2, x3. EJ depends on x1, x2, x4. And this depends on x3, x5. Now here is something important. So consider this simple tree with 3 nodes, EI, EJ, and EK, where you're given which variables each I depends on. Now please note something very important. First of all, this EJ, if EJ and EI are a parent and child, they have to share at least one variable, and they do share. They share in fact x1 and x2. Similarly, if EK was a child of EI, they have to share some variable, they share x3. But very importantly, these two cannot share a variable. Can somebody say why? I claim that every level of the tree is an independence in terms of not sharing any variables. Because suppose they share a variable, right? Then the one that came later in time, why did it become a child of EI? It could become a child of EJ. Right? Remember, we put it as the deepest. This is important. Deepest. So suppose this came earlier in time, the EK came earlier in time than EJ. EK would have been made either a child of EJ or come lower in the tree. Why was it made a child of EJ? It's not possible of EI. So a very important point is that every level of the tree has an independent set of nodes. If not, look at the ones that came earlier in time that would come even lower in the tree. That's important. Just consider this simple tree. Just this witness tree. There's nothing below it. I'm going to do a breadth first search in any order. I'm going to traverse the nodes with the last layer, then the next layer, and so on. Right? Since every layer is an independent set, it doesn't matter. There's no left right order. Okay? No left right. Right? So I can point out to you. So okay, this EJ happened, right? Why did this EJ happen? It is because of this, and this choice of x1, x2, and x4 that happened in the 0th iteration of Moser-Tardos. Right? This EJ can point to these that I was triggered. Maybe let's draw some circles. I draw circles to denote this. Right?
These other codes, I guess.
Okay. There's zero storms. Okay. Good. So
Sorry, just the x3 instead of x4 in your first column.
oh, x1, x2, x4. This EJ. Right? So this EJ was triggered by the initial choice of EJ depends on x1, x2, and x4. It was triggered, unfortunately, because this tuple of values triggered made EJ true. And look at this. Similarly, for this, we'll draw it in pink. This was triggered by this value and this value. Then you do in your breadth first search, you go up, right? And then you can say that this ER happened because of, you now move these pointers up. Right? This EI happened because of this x1, this x2, and this x3, these three names, right? Therefore, the probability that, look at this specific tree, right? The probability that this happens, it happens if and only if the green choices triggered EJ, the pink choices triggered E5, and the blue choices triggered EI. And these are all independent, right? Because all the entries in the table are independent. So the probability that the greens triggered EJ, the pinks triggered EK, and the blues triggered EI are all independent. So the probability that this tree appears is exactly this quantity. Isn't that beautiful?
Yes. It looks like
really
like magic. Okay.
Yeah.
But it's true.
It's true, right? So let's call this the weight of the tree. Let's call this the weight of the tree equal to the weight of the tree, which is simply the product of this. Isn't that really very nice? So once you see this, you can see essentially keep advancing the pointers, and given any tree, for every node, you can precisely say this was triggered because of this tuple of variables, and all of these sets of tuples are disjoint, sets of variables are disjoint. All these tuples are disjoint, right? You think about it. Now, you have this level. You have this level. I just gave you an example, but you can easily then you'll get the idea, and you just do a breadth first search of the tree from bottom up, and in any layer, just do it in any order because they are independent and there's no left or right order. Bruno, can you turn the camera?
I mean, yeah.
Wait, do you have questions?
No, I was just asking about the camera.
Okay, so let's call this the weight of the tree. Therefore, it's just the following. Therefore, by this lemma and the corollary, what we are interested in is this quantity is simply now the following combinatorial quantity T with root EI of the weight of the tree. This is it, right? This is all we need to estimate. We want an upper bound of this, right? And we need to show that that's at most this quantity, right? We're going to do this by, we're going to, let's call it some mu of like that. Let's call it mu of now. Okay, I'm going to write a recurrence, mutual recurrence connecting these multiple mu i's, and give you a beautiful solution that you can take this as your solution. Yeah, and that will give you some insight into this. Okay. That will show to you that this is a sufficient condition. So far, remember, I have not used this anywhere, right? I'm going to show that such a thing is a sufficient condition for these mu i's to exist. Okay. So let's write a recurrence for this. Okay. So let's do this carefully. So now I can erase this. Right? So more specifically, right? Let instead of mu I, I restrict to degrees of height at most for each. Right? let the height of T is less than or equal to H. Then of course mu I is the limit of this continuum. So we want, okay, so yeah. Now we have to evaluate this quantity, right? Let's do by example. Right? Suppose take an EI. So let's say take E1. Notice that parent-child relationships have to denote inclusive adjacency, right? By inclusive, I mean that EI is adjacent to itself, right? EI can be a child of itself. Okay. Suppose E1 just has two inclusive neighbors, E1 and E2, okay? Right? And suppose you're interested in this. So suppose you want to construct a tree of height at most h, not exactly, at most h, right? With root E1. Okay. Then how will you do it, right? There are four possibilities. Right? Either you can just construct E1 and be done with it, right? Or E1 can have just child E1, and then so this is at most h, and this is at most h minus 1, therefore, or or this, in fact, this cannot occur, but let's put it in a work is not a exactly. We will need to share a variable, and this layer there is not an independent set, but let's even allow this, right? And then we'll later see that by eliminating this, we'll get some further improvements. But this already, the counting here will already give us what. So notice that as far as the root goes, right? If you want a tree of height h, there are only four possibilities, right? Because either I have no children, or I have child myself, or I have child E2, or I have child both, because I'm only adjacent in the inclusive relationship to two roots, E1 and E2, right? And my children have to be some subset of these, right? Therefore, so let's write this, right? Therefore, you want a recurrence on this quantity, right? Therefore, okay, so maybe let me write this a little, push this up a little bit. Okay, so we can forget about this. We can erase this. So what is the goal? My goal is I want to show that this, of course, goal is that this mu I is less than or equal to xi over 1 minus xi. So by induction on H, I'm going to show that mu I H. Okay? So by induction on H.
Xi times, or you can do like xi times 1 plus xi plus xi squared plus something like this.
No, even simple. Yeah, you'll see. Okay, good. Okay, so you get this, right? Therefore, let's do this example. Okay, good. So therefore, mu I comma h, it can only be four possibilities. In fact, it cannot be the last possibility, right? But we can still include it. Right? Therefore, in this example, therefore, mu1 of h is equal to either the weight of this tree, which is the probability of E1, or remember, mu accounts it adds up all the weights, right? You have to add up the weights of all these trees, right? Now, the sum of the weights of all possible trees here is mu1 comma h minus 1, right? Right? And then remember, the weight of a tree is the product of all of them. So E1 will multiply each of them. The probability of E1 will multiply each of them. Therefore, this tree gives you probability of E1 multiplied by mu of 1 comma h minus 1. Similarly, because of since the weight of a tree is the product of all the probabilities of all the nodes, similarly, you will get this plus the probability E1 times mu2 h minus 1 plus the last tree, which in fact cannot appear, right, would give you mu1 comma h minus 1 times mu2 comma h minus 1, right? Because here you have to multiply all these, right? Every possible tree you get here, and every possible tree here, you have to take the product. So you have a sum of products here, a sum of products here. So you can take all the pairwise products and take all of the entire sum, right? Therefore, you get this, which of course is the probability of E1 times 1 plus mu right? Now, you see what's going on, right? More generally, right? More generally. So let E be the adjacency and tilde plus is inclusive adjacency. Therefore, more generally, therefore, the same idea, more generally, immediately you get mu IH is less than or equal to, because less than or equal to, because some cases are not possible. The probability of E1, EI, times one possibility is that EI itself is a child, that is 1 plus mu I comma h minus 1, times the product over all JSN. Here you treat the other, so this JSN NMI, right? This is the standard adjacency of 1 plus mu j comma h minus 1, right? Right? If you can show, right? So the goal is, if you can show by induction on H that this is less than or equal to something and this is less than or equal to something, then you would have completed the induction, right? Now, you just want some finite solution for the mu's, right? So now, right, suppose there exists a finite, so of course you have one such inequality for each I, for all H. Solution rewrite. So mu H is a finite positive quantity, right? Rewrite as mu I, okay, instead of xi, I'll just predetermine use y. Well, yi is mu I is a positive quantity, so it can be rewritten with this, right? Right? Therefore, suffices it, if you think about it, suffices it, the right hand side, probability of EI times what is this quantity? 1 plus yi over 1 minus yi times the product over j in I of 1 plus yj over 1 minus yj is less than or equal to this mu is the target that you want, which is yi over 1 minus yi, which if you simplify is exactly this condition where yi equals xi. I just used a different, to not confuse, right? So, I mean, it's not a priori clear what the solution of this system of inequalities is, right? It's a too complicated arrangements. But we say, if there exists a finite solution, you can rewrite it, of course, you can, you can transform it each one mu I as something of this thing, and you want, and a sufficient condition for the yi is that for all I, you have this. And if you simplify this, this is exactly this. Where instead of xi, I wrote yi to not confuse. That's it. Right? In other words, a sufficient condition that this terminates can be given can be reduced to the existence of such wiris where that's exactly this. So it gives you some kind of explanation for why, the asymmetric local lemma, Joel showed it in a certain way. But by analyzing Moser-Tardos, you get something. But by analyzing Moser-Tardos, we get even more. That's the point. As we saw here, this tree is not possible. Right? In other words, if EI appears as a child of EI, no other children are possible. Right? Therefore, in fact, you can redo. So first of all, this explains Moser-Tardos. Right? This completes the analysis of Moser-Tardos. Just beautiful stuff. Right? So furthermore, you get the following. Further, you can improve it to something like this. Improve. For example, since if EI is a child of the root EI, the root can have no other children. You can improve this recurrence by splitting them into these two cases. Mu I H. So either EI was a child of the root, or it was not a child, in which case so plus this. With this, you can improve the symmetrical level is actually sufficient condition on symmetrical level. You can improve slightly, improve to slightly improve, but still. The D plus one you can improve it mildly. Of course, assuming that D is not zero, right? But there are other exciting applications also. People showed other applications. For example, from the fact that the children have to form an independent set, right? You can, some people in physics and so on, improve that, and therefore, the analysis of Moser-Tardos gives some results that are new even in the non-constructive. But there is much more one can do. Much more we can do. Yeah. But yeah, you already get this. It's beautiful stuff.
Wow.
Yeah, it's really spectacular stuff. But the progress after Moser-Tardos was published is also very interesting. All kinds of surprising things shown. Maybe we should stop here.
We don't have a lot of time, so we have 5 minutes.
So what I'll do is maybe I'll write some short bullet points about further references you can see in some useful
That would be good.
Yeah.
Okay.
Yeah, why not?
Yes, I'm here thinking, how did they come up with the proof? Right, and I think that, you could. What do you think? Do you think that they just tried the algorithm and tried to see what was happening, and then they found that there's this like parallel?
Seems so to me, but I'm just it's such a beautiful interpretation.
Right, at some point you kind of find maybe this table, right? This table is like very useful, right?
Yeah.
Because if you just think, you want to think about this algorithm, what happens if I do this? Let's say they did that, and now they look at the table and then they see, okay, so when.
So essentially, you want to say that when you look at this tree, you see that, well, this had to happen because of the first three samplings, then it's, the later thing happens because of a precise set of disjoint variables.
No, yeah, it's true. What do we? Okay, so you want to give bullet points or?
Later, I'll leave it. Or maybe, why don't I just say some other references that you may be interested in? So to summarize, let me give some, what about the summary? So a summary would be these references. He showed that Moser-Tardos goes even much further in this paper. For instance, for KSAT, right? You know that the LL condition gives you a sufficient condition for satisfiability. Can you sample from the set, right? Can you almost uniformly sample, right? Even that is no. Almost no, right?
Almost not. Oh, that's interesting. So what you're saying is that this algorithm will provide you a witness, but there's a priori no guarantee that it's going to be a uniform witness among the available ones. But what you're saying is that you can
Even
actually
that
sample.
almost uniform is possible. Just amazing stuff. Yeah. And a lot of it is by looking at Moser-Tardos in a much more general context. Yeah. Yeah, it's really amazing stuff. So I'll stop here. Thank you very much.
Yeah, thank you, Aravind. I guess shall we give him a round of applause? Yeah, thank you so much for the lectures. Yeah, let's go for lunch. Yes. Are you good, Sunil?
Yes, thanks a lot. Thanks a lot for the lectures. It's been really interesting.
Yeah.
Should I raise the board?
Bye. Yeah, no, it's okay. Bye then. See you.
Yes. Bye.